tell us about morphism spaces between generalized complex brains.
Yeah, thank you. Let me share my screen. So please wait a moment. So I'm very glad to be invited to this talk to present my joint work with Professor Colin Leung, my PhD supervisor. So the title of my talk is the morphism space between generalized complex brains. So the background of studying morphism space between generalized complex brains is mirror symmetry. So for mirror symmetry, we can talk about the A models and B models. So for the A model side, of course, we are supposed to have the symplectic manifold X. So we have X here, symplectic manifold X. And mathematically, we can talk about the Foucault category of X, whose objects are basically Lagrangian submanifolds with flat Hermitian vector bundles. And morphisms between those Lagrangian A-branes are computed by the Floer homology. So physically speaking, this Foucault category of X is a category of Lagrangian A-branes on X. And on the other hand, we can talk about the B model side. So for the B model side, we have a complex manifold X-check here. Mathematically, we can talk about the derived category of coherent sheaves on X-check. Objects are obviously coherent sheaves. And for example, we can just take a complex of manifolds with a holomorphic vector bundle. For simplicity, maybe we can just take holomorphic vector bundles over the X-check, over the whole ambient space X-check, and we call them E0 and E1. Then the morphism space between E0 and E1 can be computed by the home sheaves from E0 to E1, and that is isomorphic to the global extension group. And of course, the global extension group is just by definition the home in the derived category of coherent sheaves. So homological mirror symmetry conjecture say that that conjecture is proposed by conservation, of course, say that if X and X-check are mirror pairs, then the Foucault category of X is equivalent to the derived category of coherent sheaves on X-check. However, in 2003, there was a paper given by Kapustin and Orlov. They discovered a new kind of objects on the A model side, and they call them the coisotropic A-branes. They expect that the Foucault category on the A model side should be enlarged with this kind of new A-branes for the homological mirror symmetry to be true. And I'll give an illustration of this kind of problem, how coisotropic A-branes emerge in the A model side using the SYC mirror symmetry picture, which says that the mirror symmetry is just the phenomenon for the T duality. So we go to the next page. So for the SYC picture, of course, we need to take a base manifold, base alpha manifold B. Get a B here, then you can form the torus bundle X-check, and also the dual torus bundle X. And we know that the dual torus can be described by the moduli space of flat U1 bundles over the torus T here. So if we imagine that we choose a Lagrangian section, so that means that for every base point B, then you get a point on the total space of the vibration X. Then you get a family of flat U1 bundles parameterized by points on the base manifold B. Then if you pack them all together, then you get a holomorphic line bundle fed along the fibers. I will denote that holomorphic line bundle to be L-check here. So a question arises, what if we choose a holomorphic line bundle not fed along fibers on the B model side? So what if we have a L-check here, but the first Chern class of L-check when restricted to the torus is non-zero? What are the objects that correspond to this kind of holomorphic line bundles? So here comes the work of Chen Learn-Chan. They try to generalize the ordinary SYC neural transform for semi-flat brains to certain kind of brains that are not flat along the fibers by the Lam transform. So under the new setting of the SYC neural transform, they write down a very explicit, concrete example of the illustration how the holomorphic line bundle with non-flatness along the fibers is correspond to a brain on the other side. So, for example, we can just pick the base alpha manifold to be R2, or you can take the flat 2 torus, but it doesn't really matter. Then you pick a coordinate, the standard coordinate, x1 and x2 here. Then you can write down an L check in the following way for the B model side. The curvature is given by dx1 wedge dx2 plus dy1 wedge dy2. And I highlight the second term, dy1, dy2 in the purple color because y1 and y2 are fiber coordinates. So you see that this is a holomorphic line bundle, but is not flat along the fibers. And under the SYC neural transform, they compute the brain on the A side, and they find that the key point is that they find a brain, but that brain is supported on the whole manifold X. So you get an X here. That is the support of the brain that corresponds to the holomorphic line bundle, non-flat along the fibers. So it must not be a Lagrangian A brain. And indeed, this is an example of coisotropic A brains discovered by Kapustin and Orlov. So after this discovery of coisotropic A brains, then there comes the work of Hitchen and one of the also student of Professor Guardiari. They try to unify the notion of A brains and B brains in the language of generalized complex structure. So let me talk about generalized complex structure. Well, because I think most of the audience here today are familiar with the generalized complex structure, complex geometry, so I better not to really go through all the details for the very basic definitions of generalized complex structure. So I may just skip several slides for talking about the definition of generalized complex structure and the definition of the brain, the generalized complex brain, and also the description of a brain. But for my purpose, I'll go to this slide.
Maybe actually, Tony, maybe it's a good idea to go through those, the definition of the brain, especially.
Oh, really? Okay, yeah. Okay, I can spend some time. Okay, let me go to the original page here. So the generalized complex geometry talks about the geometric structure not on the tangent bundle of a manifold X, but on the generalized tangent bundle. That means that is the direct sum of the tangent bundle X and the cotangent bundle. Well, just as the tangent bundle, we have a Lie bracket on the vector fields section of the tangent bundle. We also have a bracket on the sections of the generalized tangent bundle. But that is not a Lie bracket. Indeed, we have notion of that. They are the Courant brackets, and it forms the Courant algebra. But I will skip the definition of Courant algebra. We just need to know that we can also define generalized version of complex structure. So we have the generalized complex structure defined to be an endomorphism of the generalized tangent bundle, which is square to -1. And we have an integrability condition that the eigenbundles of these endomorphisms are involutive with respect to the Courant bracket. And there are two typical examples of generalized complex structure. One is the simplex structure. You can form the anti-diagonal matrix in this way. It's a generalized complex structure. And also, if you have an ordinary complex structure, we can form a diagonal matrix with diagonal entry J and minus J transpose as an example. So apart from the generalized complex structure, we can also talk about generalization of submanifolds. So first of all, we have a pair here. Just wait a second. So first of all, we have a submanifold S, and we can also encrypt the submanifold with the two form F. Then we can define the generalized tangent subbundle in the following way, that it is contained in the direct sum of the tangent bundle of S and the restriction of the cotangent bundle of X on S, with a condition that the one form, when restricted to the tangent bundle of S, is equal to the contraction of F by the tangent vector V. Maybe I will give you an example that maybe you can take the F to be 0. If you take the two form F to be 0, then this generalized tangent subbundle is just the direct sum of TS and the conormal bundle of S. Having this kind of notion, we can also talk about the brane, the generalized compressed brane, or brane in short, on a generalized compressed manifold. So it consists of a pair containing the submanifold S, and also a Hermitian line bundle L here, with unitary connection such that the generalized complex structure preserve the underlying generalized tangent subbundle. So that's the basic definition of the brane. So we can have the notion of A branes and B branes in this way. If the generalized complex structure is given by a simplex form, then the branes are called A branes. And if the generalized complex structure is given by a complex structure, of course, the branes are called B branes. We focus on the definition of A branes. So we can decode the definition of A branes in the following way. First of all, the underlying submanifold, the support of the brane, is coisotropic in the simplex manifold X. Because of this coisotropic condition, then we can have the characteristic distribution. How we call it the curly LS. It is defined by the kernel of the restriction of the omega on S. And we can also take the quotient. So the second condition is that the curvature form descends to a two form on the quotient bundle. And of course, the restriction of the simplex form also descends to the two form on the quotient bundle. And so I will denote them to be the curly F and curly omega. The last condition is that if you take the composition between the inverse of the omega tilde and F tilde, it will give you a complex structure on the quotient bundle here. So there are two extreme cases for A branes. First of all, if you assume that the support of the A brane is of minimal dimension, then it would be a Lagrangian brane. So you get a Lagrangian condition. So in this case, the curvature must be 0. That means the line bundle is flat. So this is just the ordinary Lagrangian A brane. But on the other hand, if we assume the dimension of the support to be maximal, that means space filling. You assume the S to be the whole ambient manifold X. Then implies that the ambient manifold X has a holomorphic simplex structure given by the original real simplex form and the additional curvature two form on the brane. And so now I'd like to fix some notations because they are important for the joint work with Professor Lun. Conversely, if we consider a holomorphic simplex manifold Xi capital omega, we assume a condition that the class of the real part of the capital omega is integral. Then of course we can find a Hermitian line bundle with first rank class of this one. So I call that line bundle to be L. Then I can define a space frame A brane. I call this brane canonical coisotropic A brane. And I denote this A brane to be BCC. So of course, the curvature of this brane is just the real part of the capital omega. We also have some operations on this canonical coisotropic A brane. We can just take the conjugate brane of BCC, and I will denote it by BCC bar. By conjugation, I mean that you can take the conjugate of the Hermitian line bundle L. But because we have the Hermitian metric, the L bar can be identified with the dual of L. So the brane has the curvature minus the real form of capital omega. So these two branes are very important for our work, because our work is related to the morphism space, the home space for the BCC bar BCC system. So this one relates to our work. And I will explain it later. So we go to the next page. So of course, the central question in our talk is that how to define the morphism space for coisotropic A branes in general. Do we have a mathematical definition of it? So before talking about the BCC bar BCC system, let me mention one concept defined by me and Professor Learn, that we can classify certain pair of branes as a miscible pair of branes, and certain pair of branes as not miscible pair of branes. So for a miscible pair of branes on a generalized compass manifold, we can have a systematical way to define a morphism space between B0 and B1, at least semi-classically. But this concept, I will explain this concept in details later. I will just try to give some examples to impress all of you that what's meant by the admissible pair of branes. So let us focus on the right-hand side first, the B model, this part. So for B model, basically, if we choose a pair of B branes, they are always an admissible pair of branes under certain mild conditions. By mild condition, I mean that the intersection of the two branes, of the support of two branes, should be a clean intersection. And our constructed SC home for this pair of B branes will give you the S2 page, the E2 page of local to global EXT spectral sequence for the real honest home, the global extension group. One can also refer to the work of Kaschab there. But for the A model side, so let us focus on left-hand side. Things becomes complicated because we need to study them case by case. So we start with a pair of Lagrangian A branes.
Sorry, Tony, did you say that in the B model, the admissibility condition is the same thing as the fact that the intersection is clean?
No. I mean,
what did you say?
Every pair of B branes is well, maybe yes, because I said that every pair of B branes is admissible if we assume the condition that they are intersect cleanly. Yeah, sure.
Could you explain what the exact condition of admissibility is in the B model?
Well, that is related to the foliation or the distribution on the B brane, because for B branes you always have a let me give an example. If you take a B brane, you get a support S, and because S is a complex manifold, then we always have a complex distribution, the anti-holomorphic tangent bundle of S. But if you take two B branes, that means I add an index I here, where I is equal to 0 or 1, then the admissibility tells you, I mean, the admissibility is related to the how the two anti-holomorphic tangent bundle intersect in a nice way. That's if we intersect the anti-holomorphic tangent bundle of S0 and S1, then that is equal to the anti-holomorphic tangent bundle of the intersection S, and it gives you an elliptic complex distribution on the intersection. And indeed, the central idea for the admissible pair is that we have ellipticity of this kind of intersection. So that's why for B model, well, basically every pair of B brings are admissible.
Sorry, is this this equation T01 S0 intersect T01 S1?
Yeah.
Should be equal to what?
Equal to T01 of the intersection of S0 and S1.
And what does that intersection have to be? Could it be an arbitrary subscheme? What can this S intersection be, actually? Or is there an assumption here that it must intersect in a submanifold?
Sorry?
So I'm just wondering about smoothness of SI or S, and both of those.
Well, because in our case we only talk about the B brings where the support is really a smooth compressive manifold.
Okay.
We're not talking about the general coherent sheets.
Okay, so S0 and S1 are smooth. I got it. Okay. What about S0 intersect S1?
Because we also need to have the clean intersection. We also assume that the intersection S is smooth in this case.
Okay.
Yeah. So the point is that we would like to find a complex distribution on the intersection. Well, I mean, let me assume everything is smooth. The intersection is smooth as well. Then we want to have an elliptic complex distribution on the intersection. And if we have this one, we think that we can define the semi-classical home by taking a cohomology with respect to this complex distribution. But for A model case, the things is complicated because sometimes the two there was some complex distribution associated to every brane, but when they restricted to the intersection, they don't really intersect very well, that you cannot get an elliptic distribution on the intersection. So that's why A model is much more harder to define the semi-classical home. But for B model, you always can find such an elliptic distribution, which is just the TCO1 of the intersection X. So for the A model case, if we just take two Lagrangian A brane, so for every Lagrangian A brane, there are associated the complex distribution is just the whole tangent bundle. TS0 it becomes complexified and TS1 complexified. And again, I assume the clean intersection, then you will see that the intersection of these two complexified tangent bundle is just the complexified tangent bundle of the intersection. In this case, we can define the SC home to be the Durand cohomology of the intersection S. Of course, this is not really an honest home space for two Lagrangian A branes because we know that the honest home would be computed by the fluid homology. But what I said is that this is a semi-classical approximation. If we ignore the instanton correction, and that might be a definition for the home semi-classically. And also, in other cases that we can pick two identical branes. We just assume that B0 is equal to B1. Then because every generalized complex brane associated to a Lie algebra, then in this case, the SC home can be computed by the cohomology of the Lie algebra. So now here comes a subtle case, the third case. For the third case, we choose one brane to be Lagrangian. and another brane to be the canonical coisotropic A brane. So now it depends on really how the Lagrangian submanifold aligns as a submanifold in the ambient space. Sometimes this pair is admissible, sometimes not. For example, if the curvature of the BCC brane, so now this BCC brane has a curvature, and so the support of the B0 is Lagrangian submanifold L. If the curvature of the BCC brane restricted to L vanishes, then this is the good case. This is then they form an admissible pair. However, there's another situation studied by YuTung in the paper Branes and Quantization. They assume that the curvature when restricted to the Lagrangian submanifold L is non-degenerate. Then that is a non-admissible case. So we don't have a systematic way to define at least semi-classically home in this situation. But this situation is really interesting because YuTung find that the home for B0, BCC in this situation is related to the geometric quantization. And I will also talk about it very soon. So the fourth case is the BCC bar BCC system. So this pair of branes must not be admissible. So there are some past literature studying the BCC bar BCC system. For example, the work of L. Sasso, they study this system when X is an R torus. And this case is really related to the joint work with Professor Lan. So now we'll go to the next slide. So now I'd like to talk about the relation between A model and geometric quantization. The reason why I talk about it is because this is the work of YuTung, and the work really inspired our results. So I need to talk about it first. So first of all, we have a notion quantization. Quantization is a process of trying to make a classical physical system to a quantum physical system. So in classical mechanics, usually we have the phase space. And mathematically speaking, we have a symplectic manifold, call it M omega here. The quantization process will turn this classical phase space into the space of quantum states, which is mathematically a Hilbert space, call it curly H. So traditionally, there's a recipe to quantization in mathematics called a geometric quantization. So if you undergo this geometric quantization, then you need a choice. The choice is a polarization of the symplectic manifold. For example, if M is scalar, then you can take P to be the P01 of X, the anti-holomorphic tangent bundle of X. Then you can define the quantum Hilbert space, of course, by taking the polarized sections, which means section flat along the direction governed by the polarization P. Because now we take the P to be the anti-holomorphic tangent bundle, then you get a holomorphic, you get a Hilbert space to be the space of holomorphic sections of L, the pre-quantum line bundle. And of course, if you want to adopt the half-form correction, then you need to twist the line bundle with the square root of the canonical line bundle of M. And in 2009, there was a paper given by YuTung and YuTung, and they tried to propose another recipe to quantization, a new recipe. And later on, this recipe to quantization is called a brane quantization. What's meant by brane quantization? And what is the key difference between brane quantization and geometric quantization? The key difference is the choice of the ingredients to have to undergo this quantization scheme. So instead of choosing a polarization on the symplectic manifold, then now we need to choose a complexification of the real symplectic manifold M. By complexification, we mean that we have a holomorphic symplectic manifold X, such that the M is embedded as a submanifold of, as a totally real submanifold of the holomorphic symplectic manifold X, and also the restriction of the capital omega on M gives back the real symplectic form omega on M, and also M is a Lagrangian submanifold with respect to the imaginary part of the holomorphic symplectic form. So basically, this is what they mean by the complexification. Then in this case, we can talk about the physically defined morphism space of two A-branes. The first A-brane is a Lagrangian A-brane, call it curly B. So this curly B is the Lagrangian A-brane supported on M, because M is a Lagrangian submanifold with respect to the imaginary part of the capital omega. And we encrypt this brane with the free-field flat line bundle. So now we have the first brane, and the other brane is the BCC brane, assuming that the class containing the real parts of the omega is integral. Well, I'd like to emphasize that this is really a physically defined home space at that time. Then they have a claim, they have a physical claim linking this physically defined home space to the quantum Hilbert space in the geometric quantization. So here comes the claim. So this is a claim given by Gukov-Witten and further elaborated by Gartier-Witten. It says that if we add some assumptions that the ambient manifold is not only holomorphic symplectic, but the holomorphic symplectic structure is enriched by Harvey-Claire structure, and if the manifold M is compact, then indeed we can have another morphism space, the bimodal morphism space. Because in this situation, M is a, in this situation, M would be a complex submanifold. With respect to J. So that means that the brane curly B is also a B brane. And also because the curvature of the canonical course of A brane BCC is this one. It's the real part of the capital omega, which is omega J. And omega J is of type 1,1 respect to J. That means the line bundle on the BCC is J holomorphic line bundle. So the BCC can also be considered as a B brane. So the claim is that under the assumption that X is hyperkähler and M is compact, then you can compute the A model morphism space by the B model morphism space. But we know the B model morphism space is mathematically well defined, and after computation, it is equal to the quantum Hilbert space in geometric quantization on M. As a remark, this isomorphism does not preserve the set gradings. It's only the isomorphism only preserves the set 2 gradings. So this claim is the motivation of the joint work with Professor Leung, and as we will see later.
Sorry, just a quick question. You said that the B model morphism space is the quantum Hilbert space you get from doing geometric quantization.
Yeah, but geometric quantization on M. Yeah.
Okay.
Geometric quantization on M. Because the morphism space for the B branes, I mean the B branes are on the manifold X, but the quantum Hilbert space is for the manifold M here. Then maybe I'll talk about the physical reasoning behind this claim. So the reasoning is that because we have a Harvey-Claire metric, then and for A model and B model, they are some topological twists of the original sigma model, 2D sigma model. And in the paper, it is said that indeed we have another space called the space of supersymmetric ground states. That depends on the metric. And by compactness, we can describe the A model morphism space and B model morphism space both by the single the space, which is the space of supersymmetric ground states. So what is the meaning of this curly S-to-S-Y, at least heuristically? So we need to go back to the story of general quantum field theory. In a quantum field theory, for example, we talk about the 2D sigma model. If you want to define the morphism space between two branes, then you may think of a supersymmetric quantum mechanical system because we have supersymmetry here. So by supersymmetric quantum mechanical system, we mean a triple consisting of, first of all, a set graded Hilbert space. I call it curly H here. And second, we have an even self-adjoint linear operator called H. Physically speaking, this is the Hamiltonian operator because it's the quantization of the Hamiltonian function on the classical mechanical system. And because we have supersymmetry, then we have an odd linear operator called Q. And physically speaking, this is the S2-S5 charge. That means the supersymmetric charge. Usually the Hamiltonian operator is metric dependent, but the supersymmetric charge is a topological thing. It does not depend on the metric on the ambient space. And for this triple, they satisfy certain kind of conditions. For example, the Q square to 0. That means that because the Q acts on the set-to-graded Hilbert space, that means that we can take the Q cohomology because Q square to 0. And there are some other conditions. For example, Q commutes with the H. And also you can take the adjoint of Q, and if you compute the anti-commutator, then it is proportional to the Hamiltonian operator H. There are some mathematical examples for this kind of triples. For example, you can take the Durand complex, maybe L2 completed, and you take the Q to be the Durand differential. You take the Hamiltonian operator H to be just the Durand Laplacian. Then they form this kind of triple. And similar for the Dobu complex. So now, heuristically, if we have a pair of branes, B0 and B1, and the morphism space between them should be defined as the Q cohomology. And there's another space called the space of supersymmetric ground states, because we know that the physical interpretation of the eigenvalues of the Hamiltonian operators is the energy level. So by ground state, we mean the state of zero energy. So the space of supersymmetric ground state is defined to be the kernel of the Hamiltonian operator. And if we have certain kind of Hodge theory argument in mathematics, then we can say that the home space between the pair, between the brane B0 and B1 is isomorphic to the kernel of the Hamiltonian operator. And usually when we have the Hodge theory argument, we need the compactness assumption.
Sorry, this doesn't depend on B, like, or your branes, right? This isomorphism, like there's no dependence on B0 or B0 on the right-hand side. Can you explain that?
Sorry?
So I'm just wondering, you're saying that the Homs between B0 and B0 are given by these cohomology groups, but these cohomology groups don't seem to depend on your choice of branes. Are you saying for any two branes, you have the same?
Well, the point is that first of all, we need to specify a pair of branes. And then for that pair of branes, heuristically, they associate a triple called a supersymmetric quantum mechanical system. So the curly
for
H,
any choice.
and for any choice. So curly H, the H and Q depends on the pair of branes. And then if we imagine that really exists such a triple, then heuristically the morphism space should be defined as the Q homology, and it's a topological invariant. But on the other hand, we can also define the space of supersymmetric ground state is a metric dependent space because the Hamiltonian operator depends on metric. But if we have the Hodge-free argument, then indeed they are the same. So that's why we have the claim given by Krukov-Witten, because in their claim, we assume that there is the Hilbert metric on the ambient space X. And on the other hand, we need a compactness assumption for the M. So we expect to have this kind of isomorphisms. But this is only heuristic. So now there's also another observation for the brane B and BCC. Indeed, not only the brane B, B, BCC, and BCC bar are A branes on the manifold X with respect to one Taylor form omega K, but they are also ABA branes with respect to the triple omega I, J, and omega K. So why don't we have another generalization of this notion ABA ring using the generalized compass geometry? So I can talk about the generalized hypercompact structure on the manifold X. So by definition, a generalized hypercompact structure on X is a twisted family, an S2 family of generalized compact structure, satisfying the quaternionic relations. For example, if you just pick an orthonormal frame for this S2 family, and then you call points I, J, and K, then you need I times J to be K, and etc. You have that kind of quaternion relations, and that means a generalized hypercompact structure on X. Then we can also talk about hyperbrane, a new notion that if X is equipped with a generalized hypercompact structure, then the hyperbrane is an object that is simultaneous a brane on X with respect to any generalized compact structure within that twisted family S2. So ABA branes are an example of this kind of hyperbrane with respect to a certain kind of generalized compact structure. Maybe we know that the typical examples of generalized compact structures are simplex structures and compact structure. And now we have an analogous result that there are two typical examples for generalized hypercompact structures. First, you can just pick an ordinary hypercompact structure, IJK. Then of course we have the ordinary twisted family of compact structures. Every point are compact structures, so they represent a B model. On the other hand, you can also talk about, you can maybe, if we have a holomorphic simplex structure, we can also form an S2 family. But this S2 family is a little bit different, that it has two special points, the J and its antipodal point minus J here. So these 2 points represent B models because they are really honest compact structures. However, if you pick any point except the J and minus J, for example, if you pick some point at the equator, then you get maybe the real part of the holomorphic simplex form, and they are simplex structures. So they represent A model. Or you can also take the imaginary part of the omega. And if you pick other points, other generic points except J and minus J, they also represent A models, but with possibly a non-vanishing background B field. So with these kind of notions, then we defined ABA brane to be a hyperbrane on a holomorphic simplex manifold. And we also have another notion called BBB brane. It is a hyperbrane on a hypercomplex manifold. So there are some examples. As I said, BCC and BCC bar are ABA branes. And also, if you have a J holomorphic Lagrangian brane, this is J holomorphic, and it is also an ABA brane. For the BBB brane, you can consider space ring BBB brane, and they are essentially a certain kind of Hermitian vector bundle on the hypercadent manifold called the hyperholomorphic bundle. This is a notion given by Verbitsky. And so by hyperholomorphic bundle, it means that this is a vector bundle holomorphic with respect to any kind of complex structure within the twisted family. And if you take a non-space filling BBB brane, then maybe you can have some examples as a trianalytic sobriety of the hypercadent manifold. So you may ask how, what kind of generalized hypercompact structure can be given rise by a single hypercare structure? And there was a result by Glover Sarwan that if you have a hypercare structure on X, then indeed you can have an S2 cross S2 family of generalized compact structure. And they call this family the generalized twisted space. You can think that this product of S2 sit inside the direct sum of the Lie algebra SP1 and SP1 itself. And well, maybe you can think that the SP1 is just the imaginary part of the quaternion, so that this direct sum also sit inside a bigger direct sum, the direct sum of the quaternion and quaternion itself. And the algebraic structure on this direct sum gives a notion of the split by quaternion. And if you want to classify all the generalized compact structure on X arising from this S2 cross S2 family, that means that if we pick a triple of generalized compact structure within this generalized tensor space satisfying the quaternionic relation, then indeed this kind of generalized hypercompact structure is in one-to-one correspondent to an algebra embedding of the quaternion into the split by quaternion. Then maybe you can just compute that that is equal to the SO3 cross SO3, because how you embed the quaternion into the split by quaternion, you just need to specify the standard orthonormal frame for the imaginary part of quaternion IJK. And you see how this orthonormal frame is sent to an orthonormal frame in the first copy of the S2 and the second copy. And that gives you an algebra embedding. So it's all about the rotation group of the R3. That's why you get the SO3 cross SO3 here. So it seems that there were lots of generalized compact structure arising from a single hypercare structure, but the fact is that indeed all are essentially holomorphic simplex type or hypercompact type, maybe up to B-field transform and some rescaling of the hypercare metric. So that means that we can only talk about the ABA rings and BBB rings, and essentially they are all the hybrid rings on a hypercare manifold. So now, inspired by the claim of YuTung, we want to ask the following question, and that question, and our work are really trying to answer this kind of question for some particular case. So this is an expectation motivated by the claim of YuTung. Suppose we have an hypercare manifold X, and by the previous procedure, we can try to give rise to a generalized hypercompact structure from this hypercare manifold. So we fix a generalized hypercompact structure. Then suppose we have two hybrid rings, B0 and B1. And we also assume that they have compact, maybe also clean intersection. And under these two assumptions, we ask whether there is always an SP1 symmetry intertwining the S2 family of the morphism space if they are all defined mathematically. That means that is there always an SP1 symmetry acting on vector bundle over the two sphere S2, where the fibers are just the morphism space between these two hybrid rings. So this is a central question in this talk. Because our work will answer this question in the case of the BCC bar BCC system. So I go to the next slide and show our work. So here is our theorem. So first of all, we need to fix a hypercare manifold X. And then we encrypt the hypercare manifold X with Hermitian line bundle E with a unitary connection, such that the curvature is omega J. So maybe you can also think that this is a pre-quantum line bundle with respect to the Taylor class. The Taylor form omega j on the Hardy-Clay manifold X. And then we find that there is a very mysterious, natural but hidden SP1 action acting on the E-twisted differential forms on X. And this SP1 action will have the following property that, for example, if we consider the space of zero star forms with respect to a certain complex structure in the twisted family, then the action will send to the zero star form with respect to another complex structure compatible with the SP1 action on the S2. And also, this group action intertwines the square of a certain kind of Dirac operator, the spin C Dirac operator. So why we have the Dirac operator? This is because every complex structure gives rise to a, for example, if you fix theta here, if you have a complex structure in this twisted space, then we have a spin C spin bundle. TCU1 of the X with respect to the complex structure theta. Of course, we can also twist it by this Hermitian line bundle. So we also have the unitary connection on E so that we can form the spin C Dirac operator. Acting on the zero star form on X here. So this is the main result given by me and Professor Leung, that we find such an SP1 action intertwining the square of the Dirac operator. Maybe you wonder why this format of the statement is related to the BCC bar BCC system. So let me tell you the linkage between this commutative diagram and the BCC bar BCC system. So the first application of our theorem is that, first of all, it gives you.
Wait a second. Could you go back actually?
Yeah.
Okay, so somehow I just want to make sure that I'm understanding this correctly. So could you go back to the previous slide? So you have this S2 base, and that S2 base is selecting a different generalized complex structure in your S2 family of generalized complex structures, right? So I should think of the base of this S2 base as being a space of polarizations. So we have a two-sphere of polarizations, or, well, they're playing the role, they're kind of analogous to the space of polarizations in usual geometric quantization. Is that right?
Maybe if you talk about the BBB rings, then that matches your interpretation, because for BBB rings, usually you get the polarization as the T01 with respect to a twisted family of complex structures. And then in that case, you are really trying to find the Morphism. I mean, the Morphism phase usually is defined by the sheaf cohomology of the holomorphic sections of a certain holomorphic bundle. And in that case, maybe it matches your interpretation. Yeah.
But in this, I mean, in this case, you know, you're producing a family of. Yeah. So how are you interpreting the parameter in the S2 in this case?
Well, for the because we focus on the BCC bar BCC system, then the two sphere is this one. Yeah. As I said, the two sphere.
But isn't it true though that you have this hyperkähler manifold, and you have
Yeah.
a huge family of generalized complex structures on it, right?
Sure.
And these
Yeah.
generalized complex structures, they're kind of like different topological twists. So they should
Yeah,
be
sure, exactly.
so they should be interpreted as you know, giving you these topological twists, or you could, well, I'm just saying that it could be, you could think of them as polarizations which are designed to obtain the zero modes, the kernel of the Hamiltonian,
Yeah,
or
sure.
the supersymmetric
sure.
theory, right? And so
Yeah,
you have,
yeah, sure.
so this bundle over S2 is giving you a bunch of different cohomologies with respect to different polarizations.
Yeah.
And what you would like is for there to be, I mean, you would expect that all of the geometric quantization, well, all of these cohomologies, they all coincide with a single space in some sense.
Yes.
Now,
yes.
usually, like in the work of Hitchin and Witten, right, what they required was that you have the space of polarizations, then you had a flat connection on the bundle over that space. But in this case, what's happening is that you have a rotation group that is acting on the space of polarizations, and you just want to be able to make this bundle of cohomologies equivariant with respect to that action. And that's okay. And could you go to the next slide?
Sure.
And so here you're showing that the bundle of cohomologies somehow is SP1 equivariant.
Yeah, but indeed, maybe I'd like to clarify one point. I think in general, the cohomology is not SP1 equivalent, but we need to replace the morphism space as the space of supersymmetric ground state. It is that the S2 family of supersymmetric ground state is SP1 equivalent, but not the cohomology. But if you have a completeness assumption, then you can just replace the definition of the morphism space in terms of two cohomology to the one using the kernel of the Hamiltonian operator. And in that case, you have a SP1 symmetry.
So the square of the Dirac operator, that's your Hamiltonian, right?
Yeah, sure. Yeah, that is just like a generalized Laplacian operator.
Okay, and so should I think that we have an S2 family of SUSY models,
Yeah,
or
sure.
is there one model? Oh, I see. So this.
Well,
how many Hamiltonians do we have? How many models do we have? That's what I'm trying to figure out.
Let me think about it.
Well, I would say it's really, this is really S2 family because this is really a S2 family changing from omega I to J to omega K. This whole S2 family, these are all changing. It's not the same. See, we are not. The thing is, we are not really looking at omega J. If you look at fixed omega J, then all the other complex structure are not polarizations because they're just not compatible with omega J.
Yeah.
Is that once you really look at the next page, because this now this is really, once you look at the other complex structure, this is not compatible. Then you're really looking at the other generalized complex structure, the other model. It's really S2 family of generalized complex model, or one quadratic theory, if one would say. Yeah.
I see. So I understand the fact that as zeta moves on the sphere, that you're changing the base generalized complex structure that is defining the twisted model, right? And it's defining. So the twisted model, right? The category, something like the A model or the B model, that thing is changing with the S2, over the S2. But the thing I don't understand is whether there's one supersymmetric, Hamiltonian in the background, or if that is changing as well.
I think Hamiltonian also change because we also have a S2 family of the square of Dirac operators.
Okay.
Yeah.
Okay.
So maybe
Okay.
yeah. So maybe I go to the next page.
Yep. Okay. Sorry. Go on. Thank you.
Thank you. Yeah. So now we talk about the application of our theorem for the BCC bar BCC system. So first of all, we forget about the Habit structure. We talk about a holomorphic symplectic manifold X, and we assume the class for the real part of the capital omega is integral, and we consider the A model with respect to the small omega, which is the imaginary part of the capital omega. Then we have a line bundle L associated to the canonical class for A-brane BCC. We know that we can mathematically well define the Morphism space for the BCC bar BCC system. So there are two specific points, as I said. The plus or minus J, that point you can really compute the B model Morphism space, and they are just the Tobu cohomology for a certain homomorphic line bundle E, where E is defined to be the home of L dual and L, because L dual is the line bundle associated to the conjugate brane BCC bar. Then you get the square of the L, and you can find that the curvature is just the double of the real part of capital omega. What if we choose another point except the plus or minus J? Then in the past we don't have any clues that how can we define this kind of home space. But if we, because of our work, then we are trying to propose certain definitions on the, a version of the definition of this Morphism space. Maybe we cannot talk about the cohomological level, but maybe we can use the space of supersymmetric ground state to model this Morphism space. So we need to pick a Hermitian metric on the complex manifold Xi. Then once we have this kind of metric, then we try to define the Morphism space for the BCC bar BCC system as a pair of A-branes as the index of the Dirac operator. So now we try to impose the compactness assumption and the hyperkähler assumption on the ambient manifold X, because X is automatically the support, the intersection of the support of the two branes, because the two branes are space filling. So after some computation, then you can find that if we specify, if you choose a zeta parameterizing the generalized complex structure, and we compute the corresponding Morphism space, then it will give you the index of the Dirac operator for another complex structure, but that complex structure is the action of a certain quaternion on the zeta. So there is a change of the parameter here. So the explicit form of the mu is not quite, it's not quite important, but we need to know the geometric interpretation of the action of the mu on the zeta. So indeed, the assigning zeta to mu dot zeta is just the rotation. It's a certain kind of rotation about an axis passing through the plus and minus J by pi/2. So we have two fixed points. So if we pick J here, of course, after rotation, it's still J. So the home space respect to the J is just the index of the Dirac operator with respect to the complex structure J. And by compactness, we know that this is just the Tobu cohomology. But if we pick a point K here, if we interpret the parameter as the parameterizing the generalized complex structure, then this point should be the omega K. But after rotation by pi/2, then you get another point I. And that represents the complex structure for the spin C Dirac operator. So you get this one, the index of the Dirac operator for I. So that's why our theorem has an application that because we're talking about that there was an SP1 action intertwining this kind of the square of the Dirac operator, and it induces an SP1 symmetry intertwining the kernel of the Dirac operator, and that kernel is also equal to the index of the Dirac operator. So we can interpret our theorem as saying that there is really an SP1 symmetry intertwining the morphism space between for the BCC bar BCC system. And after explaining this one, I should say that maybe someone is familiar with the hypercaded geometry, and maybe you know that there are some theorem apparently very similar to our result, but indeed they are very different. So let me tell you another theorem given by Verbitsky, one of the experts in hypercaded geometry. So Verbitsky result concerns with another kind of holomorphic vector bundle on the hypercaded manifold X, which are called hyperholomorphic bundle. And as I said, a hyperholomorphic bundle is by definition a Hermitian vector bundle which is holomorphic with respect to any complex structure J for all theta in S2. And if you read the work of Verbitsky, then you see that there is a fact that there is an SP1 action also acting on the E-twisted form on X. But that one is a natural one given by the hypercomplex structure, IJK here. So for example, if you pick the complex structure J, then you decompose the form to be the PQ form with respect to J, then the action of this J acting on the PQ form with respect to J is just the multiplication by I to the power P minus Q. Then this is very natural SP1 action acting on the E-twisted form on X. And it also sends the zero star form with respect to a certain complex structure theta to the zero star form for the eta dot theta. And it intertwines the Dobula-Passian operators. So this, I mean, apparently this is very similar to our theorem, but one should know that there are some very crucial difference that I make a table to compare and contrast this theorem to our theorem in the next page. Let me go to the comparison first. So first of all, the key difference is that so Verbitsky is trying to study the holomorphic bundle E, but in our case, because the curvature of the holomorphic line bundle in our theorem is omega J, then the bundle is only J holomorphic or minus J holomorphic. So you cannot, at a glance you cannot find, at a glance we cannot see why there is an SP1 action acting on the space intertwining the Dirac operator. And the second difference is that the SP1 action for the theorem of Verbitsky really comes from the hypercaded structure IJK. But our SP1 action comes from another triple, which is the left triple of the holomorphic simplex form with respect to J. This one, the capital omega, defined by the half of the omega K and omega I. And the third difference is that, well, in the theorem of Verbitsky, set2 gradings are preserved. But in our case, only set2 gradings are preserved. So that means maybe sometimes you get a 0 form, and then after the action, it goes to another degree. For example, 0 to n after the action. So let me give an concrete example why this is not, the set grading is not preserved. You can think that because if we want to take the J cohomology for this bundle E, then because this bundle is ample, then all the cohomology concentrate on the 0 cohomology for J. But if we take the minus J cohomology, because the bundle is no longer ample with respect to the minus J, it's negative, that the curvature form is negative with respect to minus J, then you would expect that the cohomology concentrate on the degree 2n, where n, 4n is the real dimension of X. But our theorem says that the SP1 action will transform this kind of, will intertwine this kind of space. So the SP1 action will transform the zero degree component of the J cohomology to the 2n degree component of the minus J cohomology. So this illustrates that the set gradient is not preserved in our theorem. So as I said, the theorem of Verbitsky also has an application on other hybrid rings, which are BBB rings. Because if we take space ring BBB rings, then they really give rise to the hyperholomorphic bundle, LC1 and L1. And if you take the home between them, then E is also hyperholomorphic. So if we compute the Morphism space, and is given by the global extension group, and of course this is equal to the sheaf cohomology because we have two locally free sheaves. And by the Hopf theorem, this is equal to the kernel of the Laplace operator here. So so the theorem of Verbitsky says that indeed we also have a better bundle over the two sphere, and we have an SP1 symmetry intertwining the fibers of the curly edge, the total space of this vector bundle. So maybe I'll give you a certain kind of idea of proof of our theorem. So first of all, we need to analyze the square of the spin C Dirac operator. We use the Vogler formula here. We try to decompose it into the second order term and some silver order term. So first of all, we get a covariant Laplacian. This is the second order term. And there are three terms for the silver order terms. First of all, we have a scalar curvature, but because for hypercadent manifold, the x is Ricci flat, then of course this is 0. And you also get a form for the you get a Ricci form, and you have the triple action of the Ricci form. That corresponds to the square root of the canonical line bundle, because we're trying to compute the square of the spin C Dirac operator. And the spin C bundle differ by, the difference between a spin C spinor bundle and the spin spinor bundle is the square root of the canonical line bundle. So you get this form, but this form is also 0 because x is hypercadent. So we get rid of these two terms. Then we have the last term. The last term is given by the Clifford action. This is the Clifford action with respect to a certain kind of complex structure, zeta, of the curvature term. Curvature is the omega j here. And then we try to find out certain kind of action acting on the twisted forms, and we try to see what happens if it intertwines this kind of a square of Dirac operators. Indeed, as a result, we can find a bigger group action instead of the natural SP1 action given by the IJK. So we have a group action of SP4C acting on the twisted form on X, and this action commutes with the covariant Laplacian. There is an analog of the in the case that when E is trivial line bundle, and that is the result given also by Verbitsky, that we have an SP11 action acting on the real differential forms on X, and it commutes with the Dirac Laplacian. And if you take the complexification of the real parts, if you take the complexification of SP11, it gives you the SP4C. Well, indeed, you can also enlarge this kind of symmetry to be a Lie super algebra action, but because of time limit, I think I just keep mentioning this one. I just want to say that well, this SP1 factor is generated by the lattice operator L omega I, omega j, and L omega k. And they're important in our theorem, in the proof of our theorem, because we're trying to find a certain Lie subalgebra as a copy of SP1 sitting inside this SP11. And that is a desirable SP1 symmetry. The third step is that we try to, first of all, use the naive guess of the SP1 action to see what happens. So the naive guess would be the one naturally defined by the Harvard construction IJK. So that is the role here, acting on the E-twisted forms on X. Of course, this is wrong, but it is also helpful for our proof, because if we fix the theta in two sphere, because the SP1 action on the two sphere is transitive, then we can always move this theta back to the point J by choosing an element in SP1. I call it alpha theta, or just alpha for simplicity. So alpha acts on theta to get J. So now we can send the space of zero star form respect to theta to the zero star form for J here. And then by this transformation, we try to rewrite the square of the Dirac operator in terms of an operator acting on the space of zero star form respect to J. Because originally we have, the SP1 symmetry not only intertwines the square of the Dirac operator, but also intertwine the S2 family of a space. But now we try to identify all the spaces to a single space, the space of L zero star forms of respect to J. Then what varies is only the second order operators. So I call it the delta theta here. So I want to find an SP1 action acting on here. There's the single space of zero star form respect to J, then intertwining the delta theta. And after some computation, you can see that this delta theta consists of also two parts. The first part is the covariant Laplacian, because as a result, the true SP1, because this rho is an SP1 action sitting inside a bigger group, the SP4C, and we know that the SP4C commute with the covariant Laplacian, so this part does not change, the covariant Laplacian. However, the second part changed. So originally, for the square of the Dirac operator, we have the covariant Laplacian. Also, we have a term as a Clifford action respect to the complex structure theta of the omega J as the curvature of the bundle E here. So originally, the Clifford action changed as the theta varies. But after this transformation, then you get another second order operator, the delta theta. And now the second term in this delta theta has the fixed Clifford action, Cj. But the two form varies as the theta changes. So our problem reduces to the problem that we just want to find an SP1 action trying to match this kind of Clifford action with respect to a S2 family of the two forms here. So finally, we realized that there's really such an SP1 action given by the lateral strip of the holomorphic simplex form. We can see that indeed, if we vary the two forms here by theta, then it will give you a Lie algebra action on the E-twisted forms, which is a copy of the SP1. And after integration, you get a SP1 action here. But we can re-expect this kind of SP1 action in terms of as I said, the lattice operator. So this SP1 action comes from the SL2C action, induced by the lattice triple for the capital omega here. So you can recompute them. For example, for the omega J, if you take the Clifford action of the omega J, it will give you the IH here. And if you calculate the Clifford action with respect to omega K, then it gives you the difference between the lattice operator and the dual lattice operator. And for omega I, that is the complex I acting on the sum of the lattice operator and dual lattice operator. So you get an SP1 action, and also this SP1 action preserves the zero star form for J. So it sends the zero star form respect to J back to the same space. And we can find that indeed this SP1 action really intertwines the delta theta, this S2 family of the new second order differential operators. So now we have the completion of our proof here. And this kind of analysis by using the Bogner formula and by finding by finding SP1 action and then to see what happens if the SP1 action intertwines the second order operator can also be used to reprove the theorem of the Verbitsky.
So just so I understand here, so because of the reason that in this diagram it's J that appears in the definition of the spaces, right, is just because you're always if you're computing in one of the A models or you're always defining it through a comparison with J. So you're always bringing it back to J in order to define the space. Is that correct?
I think this is just the way to find out the desirable SP1 symmetry. This is just for the ease of the proof that I just want to identify all the spaces of zero star form respect to the theta back to the zero star form respect to J. Okay,
and once you have chosen an isomorphism to the J complex, then what is remaining here? Like what I mean, you're showing here an SP1 action, but is that the full symmetry group that it's acting on this diagram?
Yeah. So now you get an SP1 action generated by the lattice operator.
So is that because you started with an SP4 action, but you used part of that symmetry in order to somehow write it in terms of
I want to find it. Yeah, sure. I want to find another subgroup of the big group SP4C, which is isomorphic to SP1. But that SP1 is different from the natural SP1 given by the IJK.
Yes.
And this SP1 action is given by the basically is given by the lattice operator respect to the holomorphic symbolic form. And it intertwines the second the S2 family of the second order differential operators.
Okay.
Yeah.
Right. Okay. So in other words, if you consider the cochain complexes together with the operator, which the operator is d/squared, but you've written it here as Laplacian just because it's can be identified with Laplacian for J.
Yeah.
But basically you have the cochain complex, which is labeled by a point in the sphere. And you have the operator, which is also labeled by a point in the sphere. And those pairs are acted upon by SP4. Is that right?
Well,
that's SP1, not SP4. Yeah, as SP4 does not add on, does not permute those operator on the SP1.
Yeah.
Well, okay. If you see, the thing is here, if you fix J to be the generalized complex structure, then you get an SP1 acting on the operators for that particular cochain complex, right? But then you could change the J to some other GC structure, and so you have a larger group of symmetry. I'm trying to understand if that picture is correct.
Why you when you fix a J, where's the SP1 acting on where?
Oh, if you look at the top line and the bottom line, you have different operators, delta zeta and delta eta applied to zeta.
Well, that should be eta acting on J, no, on the bottom. Why the eta will also send to J, omega on J?
For other elements, for elements apart from this SP1, then that may not preserve the space of zero star form respect to J. And I think maybe
no. The line that you circle there. Why is omega J in there?
Omega J? You mean here? You mean here? Or-
Yeah. No, the bottom. Yeah, yeah.
So I assume that you could compute the d slash squared on a complex, not necessarily on omega sub j, but it could be for some other GC structure. But I think if I understand correctly, he's identifying omega sub some general GC structure, and he's just using part of the SP4 symmetry to write it in terms of big J.
Yeah.
So that everything is written on the same vector space. Is that right?
Yeah, I try to write down everything in terms of the same vector space.
Oh yeah,
but,
that's
but
true. Yeah,
we don't have.
So
But we don't have.
It's not. You don't really have a whole. If you fix a J, you don't really have the whole family of. It just move everything to the particular J.
Yes.
Yeah.
So what
Yeah.
you really think about? You have a whole S2 family.
Yes.
Of a fixed big Hilbert space of all the forms. Okay, the Hilbert space is all the forms.
Yeah.
And then for each particular element in this S2, this whole the form has you pick up the zero star form for that particular J.
Yeah. Okay.
And the SP1 will move that around and then also move the corresponding direct square operator around.
Yeah. Yeah. Okay. Yeah. Thank you.
Yeah, and I think as a result, but I mean, we can only have a copy of SP1 sitting inside the SP4C, playing the role that it intertwines the desirable S2 family of the square of Dirac operators. Maybe I should also try to make another comparison of the related work given by Ali. That, but maybe I would say that there's another application for our theorem onto the geometric quantization on the hypercaded manifold. So in our setting, we can consider a compact hypercaded manifold X, and then we try to assume that the omega j is the omega j represent an integral class, so that we can find a pre-quantum line bundle. So maybe we put that again. We just assume that there is one Taylor form representing an integral class, so that we have a fixed quantum line bundle L here. So for the traditional geometric quantization, we need to choose a polarization. So that is the T01 of X respect to J. And of course, you get a quantum Hilbert space as the space of a holomorphic section on the L. And if you scale the omega J by K, then of course you can get a quantum Hilbert space at level K. So now, assume that the K is just even scaling factor. K is even, and then we take a half of K, you get a K0. Then there associate a A-Bay ring, which is the BCC at level K in this way. Because we really have the line bundle L, then you can take the tensor power up to the power K0, then you get an A-Bay ring here. Then you can also compute the Morphism space between the, for the BCC bar BCC system with respect to the scale of the Taylor form omega K. And by our result, because we have the S-Billman symmetry intertwining those spaces, then we can see that this A model morphism space is isomorphic to the B model morphism space with respect to J. And other computation, this is really the quantum Hilbert space in the geometric quantization. So we have a parallel story. We have this kind of application is kind of parallel to that for the Google written, that they consider the BCC system, but we consider the BCC bar BCC system. And I know that because there's also related work given by Anderson, Maluza, and Beidou, that they consider the so-called the SP1 symmetric hypercaded quantization. Because Ali is one of the audience, and he also invites me to this call, so I would like to talk a little bit about their work and try to compare the work with our work. So in the setting, they assume that all the Taylor class are integral. So by the description of the second cohomology of X in the coefficient, in the integer coefficient, then you can see that we can find a single permission line bundle L, whose first Chern class is all the Kähler class, is equal to the all the Kähler class, because all the Kähler class must be the same. But in the setting, they try to vary the connection, the unitary connection, so that they are the Chern connection with respect to a different couple structure. So that is a setting. And they also consider certain kind of isometry group acting on the X. So this SPX is just the hyperkähler isometry. That means you have a diffeomorphism group. I mean, you have an element, a diffeomorphism of X, so that it pulls back the metric to itself, and it pulls back the complex structure I to I, J to J, and K to K. But we can relax the condition a little bit, that we also consider another group, the HKX, by studying the isomorphism, I mean the isometry group of the Riemann manifold XJ, but the pullback of I may be J, and then the pullback of J may be K, the pullback of K may be I. So there is an SO3 flexibility for this kind of elements, so that we can form a short exact sequence that the hyperkähler isometry group SPX sit inside the HKX, and the quotient group is the SO3 here. And there's a double cover, of course, of SO3, which is the SP1, and then they assume that there is an action of SP1 on X in the form that we can find an embedding of the SP1 to the group HKX here. So for their setting, they also then they pick a maximal compact connected group of the SPX here, commuting with the image of the SP1. And they have some assumption that so that they want a group, the SP0X dot SP1, to mimic the structural group of a quaternion Kähler manifold, SPN dot SP1 here. So having this kind of setup, then they also consider the lifting of automorphisms of the Hamilton, the Hermitian line bundle L. Then they consider the group of automorphism of the bundle L covering an elements for the elements inside the HK0 here. And this is a central extension here. Then with this kind of setup, they can also define the quantum Hilbert space with respect to different complex structure as the space of holomorphic sections of the line bundle here. Then they have the statement that so this is the theorem. I will go through it briefly. That because they have a bigger group, not only SP1, they have a group of the SP1 dot SP0X, and then if you pick an element eta, and then they will just transform one Hilbert space to another Hilbert space with another label, the eta applied to zeta here. But we can also find the stabilizer for a point zeta. So this one, the second copy, SP0, just fix the point zeta. Then we need to ask what is a stabilizer inside the copy, inside the factor SP1 of the zeta. So here, we know that there's a U1 subgroup inside the SP1 as a stabilizer of the zeta. So we can try to decompose the quantum Hilbert space as a module with respect to the U1 action and the action for the second group here, then by the weights. So the D is the weight for the U1 part, and the lambda is the weight for another part. And they also form a vector bundle over the two sphere, and the result says that they can find a canonical Hermitian connection, and the holomorphic cohomology use all tensor products of unitary simple SP prime 0 and super SP1 modules. I'm not trying to dig into details here because I think one of the audiences is the one that proved this theorem. But my purpose is that I want to give a certain kind of comparison for the theorem and our theorem. So I also draw a table here. and comparison and contrast between two theorems. First of all, in our theorem, we have a little bit less restrictive assumption that we only assume the one Kähler class is it's integral. But in that case, then they assume all the Kähler class are integral. And in our case, the pre-quantum line bundle is just fixed. Either the Hermitian line bundle and the unitary condition is fixed. In that case, the Hermitian line bundle is fixed, but something is varying. There's an S2 family of the unitary connections. So also the SP1 action in the theorem is assumed to come from some certain kind of isometry of X, but we don't assume any kind of isometry of X. We just find an SP1 action induced by a lattice triple for the holomorphic impact form, for a specific holomorphic impact form. But there is some trade-off for our theorem, that because we have a less restrictive assumption, we don't really have cohomological description of certain kind of Hilbert space. Indeed, our H here, H with the label zeta, is only the index of the spin C Dirac operators. In their case, they really have the cohomological description. The curly H zeta is really the cohomology of the double complex. And we don't consider extra group actions for the second factor. I mean, the factor SP prime 0x. But they consider this kind of action coming from some isometries so that they can further decompose the Hilbert space here. And lastly, they also find a Hermitian connection acting on the total, acting on the vector bundle over the two sphere. But up to this moment, we don't think of this existence of this Hermitian connection in our theorem. And maybe in the future, we can also try to figure out whether there is a Hermitian connection acting on the vector bundle over two sphere appear in our theorem. So that is basically the comparison between our theorem and the theorem. So maybe we can also go to another subtle case. So how about another system of AB rings, where one ring is a J holomorphic submanifold, and another ring is the canonical coisotropic A rings. Up to this moment, it is not known if our expectation is correct. It's not known if we can find a desirable SP1 symmetry acting on this kind of Morphism spaces. But there are some relations between the BCC bar BCC system and the B BCC system. I think that there is a physical trick called the folding trick in the paper of YuTung. And I think the central idea for that folding trick is also interpreted mathematically, maybe mathematically as the sympathetic group approach by the work of Bischoff Garfiari. So in this kind of idea, it is said that if we consider the BCC bar BCC system on a hypercaded manifold X, maybe we can just double the manifold X. Double the manifold X to a X tilde. And there is a canonical ring supported on the diagonal of X. I will call it the B tilde. And originally, the pair of the BCC bar BCC system will give you a single ring, call it the tilde BCC on the double of the manifold. And it is expected that the Morphism space for the BCC bar BCC system can be computed by the Morphism space for the B tilde BCC tilde system. Maybe on the double manifold X tilde, we can, because this is also hypercalar, if we suitably choose a generalized hypercompact structure, then the B tilde and the BCC tilde are also hyperrings. Then we can try to relate the problem of finding an SP1 symmetry for the home BCC tilde BCC. The home BCC tilde. The home B tilde BCC tilde, and relating them to the SP1 symmetry acting on the Morphism space for the BCC bar BCC system. So it gives us some kind of clues that maybe our expectation is correct in this situation. Maybe under some assumption that that is related to the infinitesimal neighborhood of the brane B tutor in the general case. Because we know that the system BCC is very important, I would like to also mention certain proposals recently trying to define this kind of morphism space. So one is the proposal by YuTung. This is a physical reasoning that we take a holomorphic sympathetic manifold, then we have notion of holomorphic polarization defined as a holomorphic projection from the holomorphic sympathetic manifold onto a complex manifold, where all the fibers are Lagrangian submanifolds isomorphic to the flat complex plane space Cn here. And if we encrypt the X with an anti-holomorphic involution, then we can talk about the fixed point set, the M, or maybe a component of the fixed point set M here. Then it serves as also a Lagrangian brane in X. Then in this situation, they said that because we have the holomorphic polarization, then the morphism space between the B and BCC can also be related to the quantum Hilbert space for the geometric quantization. So in this situation, the hypercaded assumption is missing. It's not assumed that we have a hypercaded structure on the X, but we assume that there is a holomorphic polarization replacing the role of the hypercaded metric here. And of course, I would like to also mention the work of Bischoff-Galtieri that they have a paper talking about the quantization of toric Poisson variety. But part of the paper also talk about the situation that is very related to the Gato-Witten, that we can consider the twisted cotangent bundle. So what is meant by the twisted cotangent bundle? First of all, we need to have a pre-quantizable Kähler manifold. And we encrypt this Kähler manifold with the pre-quantum line bundle LM here. Then by the work of Donaldson, we can form a holomorphic sympathetic manifold X in the following way. So first of all, we take the undying set of the X to be the cotangent bundle of M. So originally, because M is holomorphic, then of course the cotangent bundle is also holomorphic. But because of the presence of the Kähler structure, we can deform this holomorphic structure to a new complex structure, so that we can also deform the original holomorphic sympathetic structure by the pullback of the Kähler form. Then we get a new holomorphic sympathetic structure with respect to the deformed complex structure. So what is losing is that the zero section of this cotangent bundle is no longer a holomorphic Lagrangian submanifold with respect to the new holomorphic sympathetic structure, but the projection is still a holomorphic Lagrangian vibration. So with respect to the notion given by Gato-Witten, then this is a holomorphic polarization. So, and then we can also define the brane B and BCC in a suitable way that we can talk about the morphism space between them. So in the work, they try to make use of a certain notion called the holomorphic pre-quantization of the space ring BCC. So the observation is that I think that in the setting they try to mimic the geometric quantization procedure that by replacing the space of smooth section on the pre-quantum line bundle with the space of holomorphic section on a bundle on a certain pre-quantum line bundle, and then we try to take the polarization and then we try to just find those holomorphic sections restricted to the subset of leaves intersecting the brane B, which is covariant constant along the polarization. But first of all, how can we find those holomorphic sections? So there are some subtle point here that because the original line bundle for BCC has a curvature, which is the real form of the holomorphic sympathetic form. it has a non-zero CO2 part, so that, well, it does not give you really a double operator, which is square to zero. So there's no holomorphic structure on the original line bundle associated with BCC. But indeed, we can modify the connection for this holomorphic line bundle, that it is changed to another non-unitary connection by adding back the primitive of the imaginary part of the capital omega. So now we get a curvature which is the whole capital omega, but not only the real part of the capital omega. So now, because omega is of course a holomorphic simplex form, then it is a 2-0 form, then you can retake the holomorphic section. And the proposed definition is that the morphism space between the B and BCC can be computed by a certain kind of geometric quantization, that we take the holomorphic section of this new bundle, but restricted to the subset of leaves intersecting B, which are covariant constant on the formation. Having introducing certain kind of proposal on defining the system BCC, I would like to further explain the so-called folding trick explained by YuTung, which is a physical argument that why do we consider the doubling of the space? Is that, well, because for whether A model or B model, we're talking about the 2D sigma models. Then we were trying to consider some kind of string. There's a worksheet here, and some kind of string with two endpoints. One point lying in the boundary condition B0, which is a brane, and then another endpoint lies in another boundary condition B1, which is also a brane here. Then the folding trick is saying that we can just fold the worksheet, and then we form another worksheet. But after the folding, the boundary condition B0 and B1 will become a new boundary condition on one side by considering strings sending to the double target x cos x here. So I will call this new boundary condition B01. And on the other hand, here, because the string is given by the folding of an original string, so on this line, the value of the first argument of the string should be equal to the second argument of the string. That means it should ends on the boundary condition that is governed by brane supported on the diagonal. So that is the so-called folding trick. So it is expected that, it is expected that the computation of the morphism space between B0, B01 should be isomorphic to the morphism space of the new boundary condition B and B01. So that's why we have the argument before that maybe we can consider the BCC bar BCC system, and the morphism space should correspond to the morphism space on the double, on a pair of branes on the double of X here. So so the interpretation of this folding trick mathematically, let me skip some slide. I think this is the work for Bishop Guardiari. They also give a general proposal for defining the morphism space between a pair of generalized complex rings using the simplex group point. So we can think that the original case that if X is a simplex manifold, then the simplex group point has an underlying manifold which is X cross X. So in the general case, we consider a generalized complex manifold X here. Then we assume the Poisson vector is integrable so that we can find the simplex group point of X. And then we also have a Lagrangian A-brane supported on the identity bisection of this simplex group point. And it is expected that the pair of branes, a pair of generalized complex branes, B0, B01, give rise to a coisotropic A-brane on the simplex group point. And the proposal is saying that we can just take it as a definition. We define the morphism space for this pair of general complex spring as the morphism space between two coisotropic A rings on the symplectic groupoid. After this, I also like to mention certain kind of recent proposal on defining this kind of morphism space between coisotropic A rings. There was also another recent work given by Chin that he considered the linear symplectic torus. So I'll just be brief for his work that we have a linear symplectic torus. Then he tried to also double this space, linear symplectic torus, to a so-called twisted doubling torus. So the twisted doubling torus is the direct sum of the T and the dual torus, T dual, and it is encrypted with a symplectic form omega tilde, but also with the presence of B field, B here. So there are some definitions for the omega tilde and B. And in his work, it is said that for any coisotropic A ring, then they can be lifted as a certain kind of graph, as a Lagrangian A ring on the symplectic, the twisted doubling complex. So you get a Lagrangian A ring on the other side by the lifting. He proposed that the category of A rings on the linear symplectic torus can be defined as a certain kind of non-full subcategory of the Fukaya category of the doubling torus. So maybe do I still have some time?
Sure. If you need a little bit more, that's okay. Yeah. Maybe. Yeah, 8 more minutes. Yeah, that's good.
Oh, okay. So, so now because I still have some time, I'd like to explain a notion at the very beginning that about the admissible pair of rings in details. So let us first consider a pair of identical rings. So this is the work of Kapustin Lee that we can define the morphism space for a pair of identical rings, at least semi-classically. This is semi-classical definition as a Lie algebra cohomology. So why do we have a Lie algebra for such a ring? It's because that the definition, we need to, go through the definition of a ring that we have a generalized complex submanifold. Then the generalized complex structure acts on the generalized tangent subbundle, and it preserves this generalized tangent subbundle so that we can decompose it into the eigenbundles. So if you take the eigenbundle with respect to the eigenvalue minus I, then this is a Lie algebra A. Then so the work says that the semi-classical home for the pair of identical rings is equal to the Lie algebra cohomology for this Lie algebra. So what if we have two non-identical rings? So first of all, I'd like to say that there are 3 observations for the original case that we have a Lie algebra A. We also have the anchor map rho, so that the image of the A is called the capital P, and it is a complex distribution on the manifold, submanifold S. For simplicity, we assume the anchor map is constant rank. And also we have a kernel of the anchor map, I will call it N here. It's inside the conormal bundle of the submanifold. So there are some properties for the P and N. First of all, P is an elliptic distribution on the submanifold. So that means that if we take the foliated cohomology with respect to P, then it is an elliptic complex. Or equivalently, we can rephrase this condition as the sum of P and P bar span the whole space, the complexified tangent bundle of S. So this is the first observation for the Lie group algebra A. Another observation is that Well, the N is P modules. This is a P modules. That means that we can find a flat P connection acting on the bundle N. And also, of course, the trivial bundle has a trivial flat connection. When restricted to P, then you get a flat P connection. So the trivial bundle is also P module, but we can also rewrite the trivial bundle as the home of the L to L, where L is the line bundle associated to a brane B here. And also the third observation is that, well, indeed we can compute the cohomology of the, we have an approximation of the cohomology of the Lie algebra given by a spectral sequence. The E2 page of the spectral sequence is cohomology with respect to P, with values in the wedge, in the exterior algebra of the dual of the N here. So we try to, find some similar properties for the general case that when we have two non-identical branes, can we find such a P here, an elliptic distribution on the intersection, and can we also have some certain kind of P modules, and then can we define a semi-classical home? So that's why we have the notion of admissibility. So now I have two branes, maybe not identical. I have B, C0 and B1. So I is equal to 0 or 1 here. Then I write down the Lie algebra, and I try to write down a short exact sequence where the PR is the image of the anchor map and the NR is the kernel of the anchor map. And I also can take the intersection of the image, the P0 and P1. I got a single P here. The P is a distribution on the intersection. And we also have the intersection of N. So we can show that the N is a P module, and there's a lemma that we can also compute that. We can also prove that the home from the restriction of L0 to the restriction of L1 is also a P module. But this is really only a Pointmaster argument, linear algebra argument. So I will skip the proof. But the point is that sometimes for example, for A model, as I said, we cannot have the ellipticity of the intersection P here, so that we cannot get a desirable cohomology that match the expectation in the physics. So what we try to define the notion of admissible pairs of branes by saying that we need to have the elliptic condition, the ellipticity of the intersection P. So that's why I said for B models, we always have the ellipticity, because the P0 and P1 are just the T01 and T01 of the first submanifold S1 and the T01 of the second submanifold. So we get the intersection as the anti-holomorphic tangent bundle of the intersection. So for this kind of admissible pair, then we can define the semi-classical home B0, B01, B01. B0 to B1 as a certain kind of P cohomology with value in the home from the restriction of L0 to the restriction of L1, and twisted by the exterior algebra of the dual of N. Well, indeed, we need a certain kind of correction by the spin structure, but because of time limit, I would like to skip this part. So let me just give a very, very brief summary about our framework. That I will just go to the last page here. So this is a summary for our expectation on the desirable S-triple action acting on the morphism space between hybrid branes. So the first case is the case of BBB rings. As I said, a theorem of Bisky shows that indeed
Oops, I think you just got muted. Okay, but again, the existence of the SP1 symmetry, this is, this part this diagram here with all these cases, this is of course in the hyperkähler case where there are kind of unexpected SP1 symmetries.
Mhm.
But,
Yeah.
but somehow there's this SP1 symmetry is always part of this larger SP4, right? It's just that the SP4 doesn't act on this particular Hom space. Like once you fix the branes.
Yeah.
I see. Okay.
No, but in the case of Lagrangian, you also get it. There's also a SP1 symmetry.
And that's if you're in a hyperkähler?
If you're in hyperkähler, yeah.
Right.
You don't need to be a space filling, yeah.
I see. Yeah, that makes sense. Okay. Tony, are you back? Can you unmute yourself?
I'm back.
Okay, so you can now complete your talk because we need to clap and I need you to end the talk in order to clap. So end the talk.
Yeah, I've said that this is the end of the talk. I'm sorry. Maybe I.
Okay, so thank you. So you left right before we were going to thank you. So thank you so much for giving like a really well presented, very well constructed overview of the entire subject. Like I'm very impressed that you managed to include everyone's work. So thank you.
Yeah, you're welcome.
Would you be able to send your slides so I'll share it internally to my group?
Yeah, I think I'm able to share the slide.
Okay, so just send it to Ale in an email, and then he'll post it on our chat so that we can study it further.
Yeah, perfect. Thank you.
Is anyone have any other comments or questions before we
Yeah, I wanted to ask something. Have you thought about any specific examples? And particularly what I have in mind is the Hitchin system, which is kind of a case that was eluding from my work with Anderson and Rambato, because in that case, the symplectic forms have different cohomology classes, right? So you don't have this explicit SP1 action by isometries. I was wondering if you have thought about that case that seemed to fit in your picture.
I think that before we haven't considered this kind of problems, but maybe we can really go through details for that case and see whether there was further application of our theorem. But up to this moment, I cannot say anything. I mean, I cannot say the details.
Yeah, maybe you guys should talk about this. I mean, it's like a perfect thing for you guys to talk about.
Yeah, absolutely.
Yeah.
Can you go back to the comparison, Tony? The comparison between your work and Ale's work?
Yeah. Here.
Right. So in the case of the Hitchin system, the first assumption on the left is not possible, right? Whereas
that's right.
Whereas the corresponding one on the right hand side is fine.
Yeah, because in that case you have that omega j. I think it's a generator of H2, but omega I and omega k are trivial.
Mm-hmm.
Yeah.
But in the Hitchin system, you would be considering two hyperholomorphic bundles, or hyperholomorphic Lagrangian, or which example would you be particularly interested in?
Yeah, I'm not entirely sure. We'd have to think about it.
The space filling brane, you have the Hitchin section, you have the Lagrangian fibers of the Hitchin map.
Yeah, so the thing is, you do have you have a holomorphic symplectic structure on the Hitchin system that really just comes from the topology, from the connection viewpoint. You have J and you have omega I minus I omega K, or whatever multiple you want to take of that. And then that is completed to a hyperkähler structure once you put a Riemann surface structure on the base surface. And so yeah, you start talking about Higgs bundles and so on. So yeah, I'm not really sure. And the thing is, the pre-quantum line bundle for there are natural pre-quantum line bundles defined for all real parts of this complex symplectic form, this omega c, which in this language would be omega k plus I omega I. Sorry. Yeah. And so yeah, and yeah, I don't know. I would have to think about it a little bit more. Yeah.
Okay, so Tony, send us those slides, and then maybe maybe we can discuss this further and see if we can we'll try to understand kind of the details of your paper with Conan and see.
That's right. Yeah, sure.
Okay, let's close for today. And actually, what we could do, because we're planning to have a few more talks next term in January about this kind of geometric quantization, or especially brane quantization. What we'll do is we'll send Tony the email announcements just in case he wants to attend also. I know that the time is not ideal, but maybe at least we can send the link to the recording, and so that you'll know about this.
Yeah, thank you. I think it must be a good opportunity for me.
Yeah, the problem is just the time of day. You don't want to be waking up in the middle of the night. Okay, so thanks a lot, and let's so until next time, have a good rest of December.
Yeah, thank you.
Year.
Yeah.
See you.
All right, see you. Yeah.
Thank you
bye-bye.
again.
Bye.